All right, what if I told you that you could take a super slow, plodding search and turn it into a lightning-fast scan, just by thinking a little differently about memory? Well, today we're going to dive into one of the most classic problems in all of programming, two-sum. Seriously, this thing is a perfect masterclass in understanding the fundamental trade-off between time and space. So, you know what? Let's just jump right in with a really simple example to see what this actually looks like.
Okay, let's make this real. Have a look at this list of numbers. 2, 7, 11, 15. Can you find two of them that add up to 9? Yeah, you probably spotted 2 and 7 pretty fast. And if you did, hey, congratulations. You've already solved your first two-sum problem. Now, it seems simple, right? But how would you tell a computer to do this, especially if the list had, say, millions of numbers?
So here's the official, formal definition. We're given an array of numbers, and we're given a target value. Our job is to find the positions, the indices of two numbers in that list that add up to the target. And here's a really crucial detail. You have to use two different elements. You can't just add a number to itself unless it actually appears twice in the list.
So, where do we even begin? Well, with just about any problem like this, the best place to start is usually the most direct, most obvious approach. We call it the brute force method. And this is going to be our baseline for everything else we look at. The idea here is honestly about as simple as it gets. Imagine all the numbers are in a big, long row of boxes. We're just going to point to the first box, and then one by one, we'll pair it up with every single other box to its right. It's super thorough, and it's guaranteed to work, but as you're about to see, it is not exactly what you'd call speedy.
This breakdown shows the logic perfectly. You've basically got two loops, one inside the other. The outer loop picks a number. We'll call it our anchor. Then the inner loop goes and pairs that anchor with every single number that comes after it, checking the sum each time. If we get a match, great, we're done. If we go through all the pairs for that anchor and find nothing, the outer loop just moves our anchor to the next number, and the whole process starts all over again.
And boom! Right there, that is our very first trade-off. The time complexity here is O(n squared, which, in plain English, means that if your list doubles in size, the time it takes to solve the problem gets 4 times longer. Yeah, gets slow, and it gets slow fast. But look at the other side of the coin. The space complexity is O(1), and that's its superpower, right? It uses practically zero extra memory. That can be an absolute lifesaver when you're working in a really constrained environment.
Okay, O(n squared is slow. We can do better, right? So, what if we tried to bring a little bit of order to all this chaos first? Let's take a look at how getting organized can really speed things up.
This is such a classic move in algorithms. When searching is slow, a lot of the time, sorting can help. As soon as the numbers are in order, from smallest to largest, we can get way smarter about how we look for our pair. This is going to let us use a really clever technique called two pointers. Just picture it. You put one finger on the very first number in the sorted list and another finger on the very last one.
Now here's the really clever bit. We can't just sort the numbers, because if we do, we'll lose their original positions, and we need those for the answer. So as you see in step 1, first we have to bundle up each number with its original index. Then we can sort that list of bundles. With our two pointers at opposite ends, we check the sum. Is it too small? Well, we need a bigger number, so we just nudge the left pointer one step to the right. Is the sum too big? We nudge the right pointer one step to the left. We just keep closing the gap until we either find our target or the pointers cross each other.
And check it out. Here's our new trade-off. The time complexity is now O(n log n). For a big list, that is way, way faster than O(n squared. The main bottleneck now is just the time it takes to sort the list in the first place. But notice the cost. To get that extra speed, we had to use extra memory, O(n space, to keep track of all those original positions. We traded memory for speed. It's a classic bargain in programming.
So we went from slow to pretty fast, but can we go even faster? Can we actually get this down to linear time and O of n solution? The answer is a big yes, if we're willing to lean even more heavily on memory by using a really, really clever trick. This one question right here is the entire key to the fastest possible solution. As we look at each number in our list, we don't just see that number. We can instantly figure out the other number we would need to hit our target. We call this the complement. So if we're looking at a number x, its complement is simply target minus x. The big question then becomes, have we already seen that complement somewhere earlier in the list?
This is where our little notepad comes into play. In programming, we'd call this a hash map or a dictionary.
It's a data structure that is absolutely brilliant at one specific thing, giving you answers almost instantly. So as we walk through our list, every time we see a number, we can jot it down on our notepad, along with its location, its index. Then for the next number we look at, we just have to take a quick glance at our notepad to see if its complement is already written down.
Okay, and this is the most elegant version of the solution because we do it all in a single pass. Here's how it works. For every single number, we first check our notepad. Is the number we need, the complement, already there? If it is, bam, we're done. We found it. If it's not there, okay, no problem. We just add the current number and its location to the notepad and then move on to the next one. You got to notice that order, though. It's absolutely crucial. We check first, then we add. That's the secret sauce right there. That's what stops us from accidentally using the same number for both parts of the pair.
And what's the result of all this cleverness? An expected time complexity of O(n). That basically means we only have to look at each number in our list about one time. It is blazing fast. But, of course, there's no free lunch. The space complexity is O(n) because in the worst-case scenario, our notepad might have to hold every single number from the list. We've totally maxed out our speed by being willing to use more memory.
Okay, so we've looked at 3 totally different ways to crack the same problem: the brute force way, the sorting way, and the hashing way. Let's put them all side by side so we can really get a feel for when you'd use each one. This table just sums it all up perfectly. Brute force, that's your pick when memory is ridiculously tight, or maybe if your list is just super tiny to begin with. The sort and pointers method, it's awesome if your data is already sorted, or if you need a guaranteed time performance without any asterisks. But for the huge majority of cases, when you just want the fastest answer and you've got some memory to spare, the hash map is the undisputed champion. It is the default go-to solution.
So why do we spend all this time dissecting one seemingly simple problem? Well, because it's never really been about just finding two numbers. It's about learning a way of thinking, a way of analyzing trade-offs that's absolutely critical to being a great developer.
If you ever find yourself in a coding interview, this question is pure gold. Nailing it shows that you deeply understand that core trade-off between time and space. It proves you know fundamental patterns like the complement trick, and it gives you a chance to show that you're thinking about all the weird edge cases. The real pro move is to start with the fastest hash map solution, and then be ready to discuss the other approaches as alternatives based on different constraints the interviewer might throw at you.
So I'm going to leave you with this final thought. It's never just about finding the best algorithm in a vacuum. It's always about finding the best algorithm for a specific set of constraints. So, given these limits, 1 second of processing time and 1 gigabyte of memory, how would the size of your list of numbers change which method you choose? Thinking through that, well, that's the real heart of algorithmic problem solving.